So today we have a very interesting geometrical problem. We take a square ABCD and draw its diagonal joining the points B and D. Now we inscribe a red color semicircle so that the semicircle is tangent to the diagonal that we have drawn, and also the semicircle is tangent to the base side of the square at the point C. Now we inscribe a yellow color semicircle so that the semicircle is tangent to the side AD, and also one end of its diameter is the same point where the red color semicircle is tangent to the diagonal. Okay, so this was the arrangement of this diagram, and now the question over here is to prove that the radius of both of these semicircles are equal. So this is Anmol, and now let us see the solution. How can we prove the given relation? Okay, now let us start with the solution. So the first thing that you can notice is I have marked some of the points inside the diagram. So let me just clarify them. So the point P and the point Q are the center of this yellow and red semicircle respectively. The point where the diagonal of the square is tangent to the red circle has been marked as the point M, and also don't forget that the end of this yellow semicircle is also the point M. Now the point where the yellow semicircle is tangent to the side AD of the square has been marked as the point N. Okay. Now the first thing that we are going to do is we are going to take the radius of the semicircles as variable. So let the radius of this red circle, that is going to be from the point Q to C, be equals to a variable x, and the radius of this yellow semicircle, that is going to be from the point P to the point M, be equals to a variable y. Now we can see that the question over here is to prove that these semicircles have same radius. So as we have taken the radius of these semicircles as x and y, so we need to show that x is equals to y. We need to show this particular equation. Now in order to show this particular relation, the first thing that we are going to utilize is that the semicircles are tangent to some of the straight lines. So first of all, we can see that the red semicircle is tangent to the diagonal of the square at the point M. So I'm simply going to draw the radius from the point Q to M. And as we can see that the semicircle is tangent to a straight line, hence the angle form over there would be 90 degree. Because of the theorem, the angle form at the intersection of the radius and the tangent line is always 90 degree. And also we can see that QM is the radius of the red semicircle, hence it would have a length equals to x. Now take the yellow semicircle, and we can see that the yellow semicircle is tangent to the side AD at the point N. So if I will draw a line segment from the point P to N, it will turn out to be the radius of the yellow semicircle, because it is a line segment from the center to the circumference, okay? And this angle over there would be 90 degree. Because of the theorem, the angle form at the intersection of the radius and the tangent line is always 90 degree, okay? Now as the line segment PN is the radius of the yellow semicircle, therefore the length of this line segment would be equals to the variable y. So here we have utilized two of the tangent points. Now let us utilize the third tangent point, that is at the point C. The red semicircle is tangent to the side DC at the point C. Hence the angle over here would be 90 degree, because QC is ultimately the radius of the semicircle. Now what I will do is I will simply draw a line segment from the point D to the point Q. Now look carefully, this right angle triangle and this right angle triangles are congruent to each other because of right angle, common hypotenuse, and these two sides equals to each other because they are the radius of the same circle. So once two triangles are congruent, rest of the things between them become equal, and therefore the length of DC would be equals to the length of DM. So the length of DC would be equals to the length of DM. Now DC is ultimately representing the side length of the square ABCD. Okay, now to get the side length of the square as a variable, first of all what I will do is I will mark this particular point as the point E. Now the length from B to E, I will take it as a variable Z, okay? Now the length from E to Q is the radius of this red semicircle, hence it would have a length x. Therefore the complete length from B to C can be justified as BE plus EQ plus QC, and that is equals to BC, and this thing will simply turn out to be Z plus X, and that would simply turn out to be 2x plus Z, and this is the length of BC, that is the side length of the square. So here we have got the value of the side length of the square, and that is 2x plus Z. Therefore the length of DC would be equals to 2x plus Z. And recall that we were having this equation that the length of DC is equals to the length of DM. So if the length of DC is equals to 2x plus Z, the length of DM would also be equals to 2x plus Z. So the length of DM is also equals to 2x plus Z. Now look carefully on the line segment DM. We can see that the line segment DM can also be written as the length of DP plus the length of PM. Okay, the length of PM is the radius of this yellow semicircle having a value y. So the length of DM is 2x plus z. This thing equals to DP plus PM, that is having a value y. And if I will just subtract y from both of these sides, the value of DP will turn out to be 2x plus z minus y. So here we have got the length of DP, and that is 2x plus z minus y. Now we are going to keep these things as it is and mark some of the angles. So first of all, I will just take this particular angle, that is the angle DBC, as a variable theta. Now look carefully, as the quadrilateral ABCD is a square, therefore the side length BC would be parallel to the side length AD. So AD is like this way and BC is like this way, and these two are parallel to each other. And if there is a transversal cutting them both, then by alternate interior angle, this angle would be equals to this angle. So already we have taken that angle as a variable theta, that is this particular angle, and that has been taken as a variable theta. Therefore by alternate interior angle, this angle would also be equals to theta, and in this diagram that angle is over here and it would also be equals to theta. And this is because AD is parallel to BC, and by the property of alternate interior angles that are always equal. Okay, now take the triangle PND. So the triangle I'm talking about is PND, and it is very nicely over here. So let me just draw that triangle. So the triangle is like this way. Here is the 90 degree and that point is N. Let this point be P and let this point be D. Okay, and the value of this particular angle is equals to theta, that we have just seen how it is. The length of PN is equals to the radius of this yellow semicircle having a length y. The length of DN is nothing, so let it be DN only. And the length of PD we have just got in this particular equation, that was 2x plus z minus y. Okay, now we are going to take one more triangle, and that is the triangle BMQ, and that is very nicely placed over there on the top. So the triangle is like this way, and it is a right angle triangle, and the point where it is 90 degree is the point M. Let this point be B and let this point be equals to Q. So now we can see that the length of MQ is the radius of this red semicircle, hence it would have a length x. The length of BM we have not found as anything, so let it be BM only. And the length of BQ is equals to x plus z. Look carefully in this diagram, BQ is from here to here, and in the middle we have the point E. So ultimately BQ can be written as BE plus EQ. The length of BE we have taken as a variable z, and the length EQ is the radius of this red semicircle, hence it would have a value x. Therefore the length of BQ will simply turn out to be x plus z. Okay, and don't forget to mark the angle. So according to this diagram, the angle MBQ is equals to theta. So over here also the angle MBQ is equals to theta. Okay, now let me ask you a question. What can you say about these two triangles? We can see that both of these triangles are right angle triangles first of all, and they have one equal angle, and that is equals to theta. So you can just use two things. First one is similarity. You can just make these two triangles similar to each other because of angle and take the ratio of their sides. And the second one is trigonometry. So I'm just going with the trigonometrical because that is more easier. So in the right angle triangle PND, the value of sine of theta will simply turn out to be height upon the hypotenuse, and therefore sine theta will turn out to be y upon 2x plus z minus y. And in this right angle triangle, that is the triangle BMQ, the value of sine of theta will turn out to be again height upon the hypotenuse, and therefore x upon x plus z. So now we can simply compare these two equations because both of them are equals to sine theta. Therefore y upon 2x plus z minus y is equals to x upon x plus z. Okay, so we get this particular equation. Now what if we have made these two triangles similar to each other? So if we have made these two triangles similar to each other, and according to the correspondence, if we have taken the ratio of their sides, you will also get this same equation. Okay, now to simplify this equation, what I will do is, first of all I will do the cross multiplication. Therefore on the left hand side I will have y into x plus z, and that is yx plus yz, and this thing equals to x into 2x plus z minus y, and that will turn out to be 2x square plus xz minus yx. Okay, now to simplify this equation, I will move xy from the left hand side to the right hand side and xz from the right hand side to the left hand side. So I will get yz that is already in the left hand side as it is minus xz that I have shifted from the right hand side equals to 2x square as it is minus yx. These are the terms that were already in the right hand side. Now negative yx that we have brought from the left hand side. So now we can say that negative yx and negative yx will simply turn out to be minus 2 times yx. Okay, so now we have this particular equation. Now to solve this thing, what I will do is I will just move negative xz on the other side and negative 2yx on this particular side. So I will get yz plus 2yx equals to 2x square plus xz. Okay, now on the left hand side, from this both terms I can take y common, so inside the bracket I will have z plus 2 times x, and on the left hand side I can take x common, so inside the bracket I will have 2 times x plus z. Now as the variables x and z were representing some of the side lengths, therefore the value of 2x plus z cannot be equals to 0. And why I am saying this thing, because this bracket can be simply factored out from both of the sides, and when they are cancelled out, what we are finally remaining is with x equals to y. And finally, according to this arrangement, we have seen that these both are equals to each other, and hence we have proved that the radius of these two circles are same. So this was my way to solve this particular problem. If you have any other method other than this, do comment below, and if you want to share any kind of picture related to a solution or a problem, you can email me, or else you can send it to me on my Instagram. The link is in the description.